So now we're going to look at properties of integrals. The first property of an integral states that if we flip the limits of integration, or our upper and lower bounds, so if we're going from b to a rather than a to b, then we can just flip the sign of this integral. So generally, integrals need to go from a lower to an upper bound because we're traveling along the x-axis, or whatever our variable is, in a positive direction. However, if we flip those bounds, we can go from, let's say we're going from 3 to 1. And we have some function. We're integrating with respect to x. This is just negative, and then the integral from 1 to 3 of this function with respect to x. Okay? Number 2 states that the integral from a to a of f of x dx is equal to 0. And doesn't that make sense? Because if the integral is telling me the area under a curve, and the width of that area is 0, because I'm going from a to a, which really means I kind of am finding the area of a line, that's going to be the area of 0. If I've got the integral of a constant, that tells me that this is going to be the constant times my upper minus my lower bound. And let's see why this makes sense. Because if I have a function that's a constant, then what does this look like? This really looks like a straight line. So let's say I have the function 2. Well, this is really y equals 2. Let's say that this is y equals 2. And let's say I'm going from an a value of 0 to, maybe this looks like 3. Well, what's this area going to be? This area is really just going to be 2 times the difference between 3 minus 0. That's just going to be 6. So that's what we mean by this. All right, then we've got, and number 4 and number 6 are pretty similar. These are the sum and difference rules for integrals, and they just state that if we're finding the integral of a sum of 2 functions, it's just the sum of 2 of those integrals. Same idea with number 6. If I'm finding the integral of the difference between these functions, it's just the difference of those integrals. This is kind of similar to our sum and difference rules of derivatives, if you remember that. Okay, number 5 just tells me that if I have a constant times a function, I can pull this constant out to the front of the integral. So I can take this c and I can pull it out to the front of the integral. Okay, and number 7 tells me that if I have a function that goes from a to c, then I can split this up into 2 integrals from a to b and from b to c. So if I have some curve, and let's just put this in the first quadrant for simplicity, and let's say I'm going from a to c, and I don't know, maybe I have some curve that looks like this. This is my curve. I'm going from a to c, and I'm finding this area under my curve y equals f of x, right? And well, I can split this up at any point in between, really any point b. And I can just take the sum of the area from a to b and the area from b to c. Kind of makes sense logically. So now what we're going to do is we're going to use these properties of integrals to evaluate some integrals. In number 3, we're going to use the fact that the integral from 0 to 1 of x squared dx is 1/3. So a lot of times we're just going to be given some known integral we can work with, and the properties of integrals to evaluate the integral between from 0 to 1 of 4 plus 3x squared dx. Okay, the first thing I notice is that I can split this up into 2 separate integrals because of rule number 4. So this tells me that I can split it up into 2 separate integrals. So rule 4 tells me that this is equal to the integral from 0 to 1 of 4. Now, this dx needs to be applied to both of these terms because it's in parentheses, so it kind of needs to get distributed. So this is going to be a 4 dx plus the integral from 0 to 1 of 3x squared dx. Okay. Now, I've got, in the first integral, I've got a constant inside of my integral. And look what happens when we've just got a constant. That brings us to rule number 3. This is just going to be that constant times b minus a. So according to rule number 3, this is just going to be the constant of 4 times 1 minus 0. And so this first integral is just going to be 4. Now as for the second integral, it's not quite as simple. I've got a little bit more going on here. I have that the integral from 0 to 1 of x squared dx is 1/3. I know that. But I don't know what happens when I multiply it by this 3. However, rule number 5 tells me that I can just pull this constant out to the front of the integral. So this constant, or this coefficient inside the integral, really just becomes multiplied by whatever I get from this integral. So that's what this is going to look like. This is going to be, according to rule number 3, equal to 3 times the integral from 0 to 1 of x squared dx. Well, we're given that the integral from 0 to 1 of x squared dx is 1/3. And so now I'm just multiplying my 3 by 1/3 to give me that this is equal to 1. And finally, because these are added together, because of that sum property of integrals, well then my final answer is going to be 4 plus 1. And so this is all going to give me 5. So 5 is the value of this integral. All right, number 4. If it is known that the integral from 0 to 10 of f of x dx is equal to 17, and the integral from 0 to 8 of f of x dx is equal to 12, find the integral from 8 to 10 of f of x dx. So based on property number 7, I know that if I have an integral from a to c, I can break it up into the integrals from a to b plus the integral from b to c. And so let me draw a rough sketch of what this might look like. Now I don't know what this function f of x looks like at all, but we can just make it, well, anything we want. So let me just make this some curve, and I'm going from 0 to 10 ultimately. So let's make it look something like this. And I'm going from 0 to 10. Okay. I found that the integral from 0 to 10 is 17. So I found that this area as a whole is 17. So this area is 17 units, right? I found that the integral from 0 to 8, so let's say if this is 10, maybe this is about 8, maybe this is about 8. I found that this area from 0 to 8 is 12 units. How can I find the area from 8 to 10? So how can I find this area? How can I find this area? Well, if the total area is 17, the area from 0 to 8 is 12. If I just subtract the total area from the area of this one portion, I get the area of the other part of that curve. So this is just equal to 5. And so that's my final answer, that my area is just equal to 5. And I can confirm this using that property of integrals, which is property number 7. I can confirm that using my property of integrals because I know, according to number 7, because I know the integral from 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx is equal to the integral from 0 to 10 of f of x dx. And that checks out. 12 plus 5 is equal to 17. All right. And finally, let's just do one more. So this is a graphical problem. It's very similar to what we did before when we found the value of the integral by interpreting the integrand as an area. So this is very similar to that. So I've got y equals g of x. I want to find the integral from 0 to 3 of g of x dx. Now, if this is 12, I've got 1, 2, 3, 4 regions between 0 and 12, then this must be 3, 6, 9, and I'm going up by 3, so this must be 15 and 18 to get to 21. All right, checks out. And so let me label the rest of my y-axis too. Also, I'm going up by 3. And this is going to be -3 and -6. Okay. The integral from 0 to 3 of gx dx. So 0 to 3, I'm looking for this area. Now there are different ways I can interpret this area. I can look at this as if it's a trapezoid. I can do that. I can look at this as a trapezoid, this being my lower bound. Or I can look at it, and this is kind of what I find easier, as just a triangle plus a square. As two parts, a triangle and a rectangle. And so this triangle is going to have an area of 1/2 times the base. Well, the base is 3 units long. The height from 6 to 12 is 6 units high. And this is going to be 18 divided by 2, which is 9. Area 2 is going to be just base times height. So width is 3, height is 6. And so this is going to be 18. And so my first integral is just going to be 18 plus 9, because both are above the x-axis. And so this is going to be 27. So that's the value of my first integral. So now the integral from 3 to 12. So now I am finding this area right here, 3 to 6, and from 6 to 12. And this area down here. All right, again, I'm going to break this up into 2 different regions. So this is going to be 1, and this is going to be 2. And so region 1, for my second integral, is going to be a triangle. And so this area is going to be 1/2. The base is 3 units. The height is going to be 6 units. It's actually the same exact size of this first triangle here, which is 9 units. Okay, in area 2, now we're told that this is a semicircle. So I can assume this comes from the sphere with a radius of, let's see what our radius is. So this would be a quarter of a sphere. So a quarter of a circle with a radius of 6. And so that area is just going to be 1/4, so 1/4 times pi times 6 squared. This is going to be 36 divided by 4 times pi is 9 pi. Now I want to add these together, but one thing I want to keep in mind is that this is the area below the x-axis. So this is a negative area. This is a negative area. 6, because it's above the x-axis, is going to be a positive area. And so to find my total area, I can just take 6 and subtract 9 pi. And so that is going to be the area of that region. Remembering that an integral is just the net change of that area, that net area below and above some curve.